Okie doke. So we want to look at using technology to solve these linear programming problems. Now, I think Sage Math is a quick thing to go to. So I just typed in Sage Math linear programming. It's free. We can use the Sage cell to enter things and all that. So then I put that in, got this mixed integer Sage documentation and so forth, and I got this help page that I went to, and it kind of looks good, but it looks a little limited in that it seems to only want canonical form. I don't see anything about equality constraints there, that sort of thing, and I don't know. I just not real happy with the documentation I see here. As I'm looking at this looks kind of hard as far as trying to keep track of what they're doing. I don't think it really is very hard, but it. I don't know. I'm not happy with it. Now the nice part is, Sage Math is actually written in Python, and I think it's these days a very popular language to use for web applications and scientific applications. A lot of scientific stuff going on in Python programming. But the nice part is Sage Math is built in Python, and so it understands Python if you just type in Python, and we'll see that in a second. And so I typed in Python linear programming, and I see this, the SciPy, that's scientific Python, optimized Lin program, reference guide. Hey, that sounded like a winner, so I went there. And, well, we'll get back down to that in a moment. Let me scroll up here. So I got to this page on this thing, and notice here it has the less than or equal to, no big deal there. If I have greater than or equal to, just use negative signs. But then, here are equality constraints, and I can put lower and upper bounds. This is kind of small. And I can put lower and upper bounds on my x's. Now, this is in the matrix notation. Don't get alarmed if you haven't had linear algebra. Not a big deal. We'll see, when we look at a real problem, that it's pretty simple to take care of all these things. But here we have A, an upper bound matrix, and that's just because it's a less than or equal to, and then an A equality matrix that we'll have to give it, or not. If it's not there, it doesn't matter. And so that looks great. And notice here on the lower and upper bounds, it doesn't say anything about they have to be positive. So we could even put no restriction on x, and it would assume it could be negative. So this is really nice this way. Okay, so parameters, it tells us what each of these things is doing. Callback function, I'd have to look at that, but we aren't going to worry about it. Now, options, that might matter at some point, and then what does it return? It returns x, it returns the function value, slack variables. I don't know how much we'll even talk about that kind of stuff. If this was like an operations research class or an optimization class only, we would get into a lot more with the linear programming, but for ours we don't have that much time, so we will kind of stick to the modeling aspects of it and not so much the algorithmic aspects of it. So we come down here, you come down, and finally there is a real live example. And now notice here they got minus x0 minus 2x1 is greater than or equal to negative 4, and they're just pointing out that, just multiply through by a negative, turn the sign, and you've got x0 plus 2x1 is less than or equal to 4. And then we have, notice x1 greater than or equal to negative 3. but nothing on x0. And we're doing a minimization. Notice up here, where did it say? It's a minimization on these, so we need to put it in that form. If we have a maximization problem, we need to make all the coefficients negative to turn it into a minimization. But okay, so come down here, we see this. Now, how do they actually tell Python and Sage to do this? Well, it's all about the coefficients. So notice here they've got their C, that's what you're minimizing, -1 and 4. -1 and 4, and so they just set it up that way. A, the upper bound one, now they just have an A because there were no equality constraints. But the A, again, is just the coefficients, and it goes by rows, and so you see here a -3 and a 1. That was the -3 and the 1 there. Then, again, we had to multiply through by a negative here to make it a less than or equal to, so they have a +1 and a +2 for that row. And if we had more rows, you just keep going. And, so actually, you could take the bounds off of here, and you could have a row that was 0 and 1. Well, actually, sorry, 0 and -1, because you need a less than or equal to. But since they have the bounds in there, no need. We can just do it this way with the -3 and so forth. So we have our C, our A, a B, and that was 6 and 4, because remember we had to make that a +4. So 6 and 4, and we just put it in that way. There are bounds. 0 has none. X0 has none. X1 just had the lower bound of -3 and then none. And then we have to import this thing. We have to tell it how to do it. It won't know without us telling go get it. Get this algorithm to do this. And then here is where we tell it to actually do it, and we have our bounds, x0 bounds, x1 bounds, and we put that in like that. And now it says default is interior point, which is approximate by nature, and so down here they give an example of using the revised simplex. We'll worry more about that later. We'll maybe add it to this one. But, so does this work in a Sage cell? So, I found a Sage cell. I pulled up Math Sage cell. That's ready for stuff to be put in. So I come back here, and I'm just going to try highlighting everything. So copy. Now here I have to do a paste. Oh wait, it does say paste. Okay, paste. And notice it put spaces in there. That doesn't really matter, but it grieves me. And so I'm going to take them out. Okay, so I do that. And so there, it looks like everything's ready to go, and I say evaluate, and it appears to evaluate. Nothing's going on over there, but it didn't turn anything out. Well, that's because in the Sage cell, I have to specifically print these things. So print the result, RES. So I have to add that in, then I evaluate, and I get the same printout they did over here. I think did I get in a slightly different order? Now notice this says may vary. Interesting. Let's look again at what they get. They got -22 basically, right? Their function value -22. That's what we got. I can make this a little bigger so you can see better. So we got -22. It says the optimization terminated successfully, and we got the numbers 10 and -3 for our x0 and x1. They got also about 10 and -3. But it's interesting, we ours look better, a little better. I'm not sure why. But so we did that. Now you can, it doesn't look a whole lot different, but you can, instead of saying print, I often use instead show. And the reason for that is some things, if they're going to be typeset nicely, like functions and all that, they look better if you say show. And just to show you the difference, so this is the print. Now notice how it put them in the opposite order I did there, but this is the show, and in this case it centered it, made it a little bigger. The font is different. Now actually I like the sans serif font better, but nonetheless we have pretty much the same thing. But again, a show or a print, the show just tends to make things look a little prettier. So that's all there was to it. I just take those coefficients off of everything and I put them in this. Now, and I'll probably at some point supply some code. Now there are things I don't like. I think that's from stuff, I think it should go out first. So I would rather see something like that. And of course I would choose one of these, not both, either the print or the show. I'd probably go with the show, and it'll still run just dandy. And so we have that. Now, I don't know if things will look any differently if I say use the simplex, but let me go back here and see where it said methods revise simplex. So I'm going to highlight that and copy it and put it over here and right there, paste it and say evaluate. Oh, I didn't expect that. Unknown solver revise simplex. Let me see. Yeah, that's a interesting. So you run into something like that. One thing I could see is putting an underscore in there. Maybe there's actually supposed to be an underscore. And I hit evaluate. No, doesn't know it. And let me just try saying simplex. Evaluate. Aha! So I try that. If none of those would have worked, I probably would have gone back to Google and said something about Python linear programming simplex method, something like that. But yeah, I'll probably suggest we always put that simplex method in. Notice nothing looks different in the answer than in this particular case, but there are times, and we'll get to that when we get to networks, that it makes sense to say let's use the simplex method. And I think that's it. So that one, pretty straightforward. Again, going back to this, we'll put a link in Blackboard to this page. But they're just using these coefficients, and this is just row by row. You just have to pay attention to things like there are 2 square brackets there, and then a comma, 1 square bracket. So each row is in a square bracket and the whole thing is in a square bracket. Now that's actually a matrix, but again, if you haven't had linear algebra, who cares? That's how you tell it what these coefficients are on those inequalities. Oh, let's try one other thing. Let's make, just to see what happens, let's make this an equality here. And so that's going to change a little bit. A is only 1 row, so we have that. And B, our original B, is only one row, so I'll do that. Then I need this equality thing. I guess I could do something like AE and space equals. And then notice it's giving me a red sign there because I need another one of those. So there's my equality constraint. And then here, of course, it's not happy, so I'll also do a BE and equals. And we need to tell it that 4. Okay, so there's my, one. It's kind of boring in that they're just one row each, but hey, what the heck? We'll keep the bounds the same. We won't change those. What was the answer again? Yeah, we had this one was -3. That one reached its lower bound. That's interesting. Okay, so we have that, and we have our A upper bound was A and B upper bound was B. So now I am going to add in, so I'll copy that and paste. And so what the heck was that called again? I have to go back up here in the help. Oh, A equal. Makes sense. So this was EQ, and we put an E here, and this was EQ, and we put an E on the end of that. But everything else is the same. And so I've added my equality constraint, and it terminated successfully again. Oh, sadly, the same answer. So let's see a different answer. Let's say that has to be 0. And now we get a much different answer around -4 and 4 and 0 for that. Okay, so that definitely changed the answer. But when we had that as a -3, and you can see a little bit why that was going. Well, I'd have to go back a ways because it mentions the slack. Actually, we can look here at their output. So the original problem, here's the output. Notice it said the slack here was essentially 0, 10 to the -8th. Really 10 to the -7th because that's an 8. So 10 to the -7th, that's pretty much 0. And what that means is if that second slack was 0, it meant that this inequality was actually tight. In other words, it reached its value of -4 here. And so when I made it an inequality, it didn't change anything. So let's go back and instead of, let's make this one the equality and that one the equality and get rid of that. So now I think we should get a definite different answer than we had before. Yeah, -9 because we forced that top one to be an equality, and I guess our solution is x0 -3 and x1 -3 with a function value of -9. Okay, but pretty simple to put in. Certainly, you'll probably try to put some in and have plenty of problems at times. Sure, happens. But the general idea, pretty straightforward. Okay, so we'll call that good on using our technology. So, I was out to use Sage language, but instead I'm using Python language. But again, to Sage, they're really about one and the same thing, but not to us. Okay, so we'll call that one good.